Thank you very much, Shastri. It is, I don't think I can live up to various positive things you said. The only point I like to make is I enjoy physics. It's a great privilege to be able to study physics and work with physics. And since we have a large number of people here whom I know quite well, and I've really enjoyed learning physics from them all the time. So before I start, I want to say a few things. Shastri told me that the uh, participants are really faculty members teaching mainly in undergraduate colleges. They may not get an opportunity to teach quantum mechanics quite often, and they may not have, having not taught it for some time, they may need some amount of refresher points, which I will try to do. And I had actually aimed perhaps a little higher, so I'll try to go a little slow and see how the whole thing proceeds. Please stop me to ask questions anytime you feel like. I'll be more than happy to look at it. And there are others who are here also who will be able to comment on the main points which I'm trying to make. Okay, having said that, I would like to start sharing my screen now. And let me do that first. Where is this screen now? Okay. Wait a second, where am I? So the talk is on an introduction to weak measurement, an idea which came about 20 years ago, and I would like to present it to you people here. The overall plan is the following: introduction, a bird's eye view of the weak measurement that we will have. We have the standard method of measurement, which is the von Neumann model, about which we all know because whenever we teach quantum mechanics, at some stage we discuss a double slit experiment, and it's associated with the fact a single particle has to go through both the slits before an interference is formed, even though particles are supposed to be localized, our classical way of thinking, and so on. And so there is a model there. Then comes a new concept called post-selection and measurement. This is a concept which is very useful to our understanding of what I want to say a little later. I will deal with all this in terms of spin half systems where the algebra is the least problematic. Then finally, I will take exactly what is the weak measurement calculation wise. But before I do all that, I will start with the bird's eye view. And let me just show this slide before I proceed further. We know the process of measurement has been a subject of considerable debate ever since the development of quantum mechanics in the last century. Incidentally, yesterday Professor Alwalia gave a very nice overview of various formalisms, but all the formalism ultimately need we discuss a measurement. And that is a very debating, I mean, people are debating over it. Quantum mechanics is a very successful story, but the concept of measurement and the collapse of the wave function after measurement is still not fully settled. A model for measurement was proposed by the famous mathematician physicist von Neumann in 1935, which is the one we use regularly. The way it's a most simple example when we start teaching quantum mechanics is to perform a double slit experiments with particles, photons or electrons or some other particle. Incidentally, this kind of experiments have been done by several people now, having single particle in the system, whether it is electron scattering or whether it is photon scattering, and these experimental results have been found. These articles are there in American Journal of Physics, and those of you who have not had a chance to see it, I will strongly recommend that you look at it. There are many interesting things which we can teach the students. How do you decide that there is only a single particle in the slit? These are questions which are very nicely answered, and they are very, very simple, straightforward ones, which can be used to discuss these experiments. And okay, the apparatus, it goes there one at a time, and each of them hits the screen, and you see a scintillation count, and we observe an interference pattern only after several of them pass on the distant screen. We explain this result as an interference of a particle passing through both the cells. However, once it is detected on the screen, the particle is localized and occupies the place where it was detected. Thus, that is, collapse of the wave function has taken place, and we teach this regularly. When tries to observe the slit through which it went through, a particle went through, the interference is destroyed. This is explained very well in Feynman's book in volume 3, and he says this is the basis of understanding quantum mechanics. Okay. More recently, Aronoff, Albert, and Weidman made a new suggestion of making measurements, which is named as the weak measurement. This does not address the problem of collapse of wave function. We are not going to talk about that. This is just a new method of making measurement. We start with a bird's eye view and present a simplified version of the mathematical calculation a little later. So firstly, let me give you the bird's eye view. Consider a spin-a-half particle, say an atom with spin and magnetic moment. So here we have a picture. Is the cursor visible, Shastri? Shastri, is my cursor visible?
Yes, sir, it is visible.
Okay,
yes,
good.
sir.
So here is a silver atom beam which is going in this direction, and silver atom can be thought of as a small magnet. These are two things which are just to collimate the beam to see that it doesn't spread, and it comes here, and in the magnet the spins can be, this is a standard thing. Here in the magnet there is a non-uniform magnetic field. I'm just going over the standard thing about the Stern-Gerlach experiment here. And if the magnet is, say, pointing north, south like that, the magnetic field on the top of this side is not the same as the magnetic field here. So there is a net force acting on it because this is a non-uniform magnetic field. So if the spin were pointing up, if the magnetic moment were pointing up, it will end here. And if the magnetic moment were pointing down, it would end here. And the side beams are there mainly because on the side the magnetic field is weaker. So only in the middle the magnetic field is strong, and that is why you see such a pattern. Now, this explanation means that I just have two possibilities here, which is not what happens in classical mechanics. In classical mechanics, if the spin were pointing in some general direction, theta, making angle with the up direction, then it will travel a little less. And if it were perpendicular, there will be no force. So the entire thing would be filled up if this were a classical way of analysis. So this is what happens. In fact, this experiment was what excited many people into understanding quantum mechanics. This is the experimentalists were getting more and more convinced that quantum mechanics is the right thing to do. And this was one of the principal experiments that was done. Okay, now let us consider the following situations slowly. If the magnetic field in the SG apparatus is not strong enough to split the beam into two distinguishable beams, we will have the following situation. Here is the oven producing the beam, and the beam is collimated. Here is your varying magnetic field, and here is the X and the Z. By the way, later on when I'm doing the calculation, I will call this the Y, not the X. This is, I picked up this picture from some paper, and so they call this X, but my calculations will be with Y, as I have indicated here. Now, and this is the, you look at the cross section, north-south, and so when the magnetic field will be like that, and you can see that the magnetic lines of force here is more concentrated on the top one, so the magnetic field is large, and that's what produces the force on the magnetic moment, which is going to be, of course, part of the atom. So this is the way it will spread here. Now, let us consider the magnetic field without a magnetic field. Without a magnetic field, because there is some initial spread here, the thing will be this curve without magnetic field. Maybe I'll enlarge it a little bit temporarily, just to be sure that it's clear. Can you see it better now?
Yes, sir.
Okay, here the top one is without magnetic field. The next dotted one is a weak field. Then the last one where the separation becomes clearly visible is the strong field, when the two of them get separated. Now, let me go to a different set of possibility. This is the actual weak measurement, which was suggested by this group of people, Aronoff, Albert, and Weidman. And the idea is this. Here, I have noticed the spin of it. Okay, let me just mention, this is my z-axis, vertical. And the spin is almost normal to the world. Sorry, in this notation, okay, it is making a very small angle to the axis here. And it is coming here, and this is a weak field. So the weak field cannot separate it very much, but it comes out here, slightly turned. Okay, then having come here, here is a strong field in this direction, along this direction. So the beam gets split very much. And now you can try to calculate the spin, value of spin from here. Okay, let me go back. How will you calculate the spin here? In the first thing, you will know the properties of the various ways in which this is going to give a force. So you know the path and you know all these distances, geometry. So you measure this distance and use the coupling constant, if I can say, of this magnet with the particle, and you take that and divide this deviation divided by the coupling constant would be the spin, because the interaction would be coupling constant times the spin. And so that essentially it will be the interaction energy is mu dot B. And so that's what will cause. And since I know the B here in its own way, I will be able to find out this. So the same story is valid here. I know everything about the properties of these magnets. So I know how much this extra length is there. So based on that, I can find out the spin. It turns out in the calculation, this can become, for spin a half, normally one would have half and minus a half. This can become 100, very large. This is the matter. This is what is the first paper which was written by the group, the 3 members. Once this is the effect of a weak measurement. This is the basic idea. Once this is clear, now it's just an exercise in quantum mechanics to implement all this. So let me just wait here for a minute before I start doing the implementation to see if there are any questions. I'll just wait for a minute.
Sir, in this experiment, the initial beam is polarized?
The beam, initially, yes, it is polarized. You are right.
Okay, sir. It is polarized almost horizontal.
Correct.
Not exactly.
No.
Okay, sir. Okay.
And then it's going through the beam. That's right.
Yes.
This is, of course, with atoms. You can also do this with photons using polarization of the photon.
Sir, are we seeing this? There are 2 types of expansion, right? One is, of course, very, very large. That is along the horizontal direction, there is a huge split. And one can see that the beam is also slightly, spread along the vertical direction also.
That is actually what matters. It is the vertical direction which we will use to calculate the spin.
Okay. And this
direction.
But there are 2 magnets, right? There's one magnetic, weak magnet is there, and a strong magnet is there.
Correct. So we will apply this and apply this for the entire thing.
Right.
Okay. The rest of it is called calculation. But the calculation, there are some interesting points about the calculation. All right. So I'll just wait for another 10 seconds and then perhaps start. So the first thing I will do is von Neumann's model of measurement. We now will start in a systematic way. The system is represented by S. In this case, the atom And the measuring device, which is the CERN-Gelrach experiment for us, is by D. It is a detecting system. The observable to be observed is measured is by a Hermitian operator A. That is the observable that is going to be measured. And the act of measurement and observation of one of the eigenvalues of A. And this is recorded by a detector variable, which we will call Q. So let's be clear. I have a system S, which has, for our case, it will be SZ. That will be the operator. And for the detector, it will be the pointer, that is Q, is the coordinate displacement of the particle on the screen. That will be the thing. So the device and the system need to interact, and we take it as an example of the interaction Hamiltonian to be this. The Hamiltonian consists of two parts, and they are a direct product space. This is the strength of the interaction, which will depend upon the variation of the magnetic field and so on. And of course, it will depend upon time, because as the particle is traveling, the magnetic field it sees is keeping on varying. And now I write down A, which is our case of sigma Z. And this one which I have is the momentum operator of the particle which is moving. So that is what is being used for counting. And since QP is I, Q will change. And GT denotes the strength of interaction. We will simplify it, assume the particle passes very fast, because for calculational purposes, it is easier to do this. Otherwise, you will have to do the full thing, perhaps numerically. Okay. Now let us see how Q, the observable in the thing, changes. This is the thing which we calculate in undergraduate physics, right? We apply the force and the distance traveled and find out how much it happens and what angle it emerges, and then it goes to the screen, and then geometry will tell you how far it will go up in the up direction. So here you are writing everything quantum mechanically. The change delta Q for the observable Q is due to the Hamiltonian given for the system, for the detector, and the system detector. Now, the change here is given by the standard equation. Notice everything is being written in Heisenberg representation. So I write it in this form. dq dt is given here. Now, Q, as far as the system is concerned, this is a variable associated with the detector, is 0. So HS acts only on the variables of the system. Further, we assume T0 to be so short that this contribution is also negligible because of the GT negligible, the short enough to give an integrated effect much like an impulse. So on the other hand, Q dt, this one is negligible. As t goes to 0, the contribution for this will be 0, because this is a finite quantity. Whereas on the other hand, I will have GT is the only one which will survive, and that will give me integral GT A cross PQ, and that will be I, PQ is ID. So for the detector, it is this. So this is how delta Q is going to change. Now let us see the interesting part. So this change occurs only coming from the term HSD. All other terms will not contribute. Okay, now let me go to this. Let us say the device is initialized into one of the eigenstates of Q. Let us say eigenvalue Q. The state of the device is given by this wave function, ket Q. I put D to indicate that it is of the detector. It is in the space, in the space of the detector. If the state of the system is an eigenstate of A, given by AJS, S plus D would become, after measurement, after this, e to the ij cross P. This is the time development of the system, because this was the Hamiltonian. And when I do that, I get AJS cross QD. This is the Hamiltonian. It is minus IH integral dt So G integration is the only integration. That delta function just gave me this. And then I have A cross P is here. AJ, this when it operates on A will become AJ. IS cross P. This should have been AJ IS cross P. Right? And Q. Now, this operator that I have is essentially a displacement operator for P. Pardon?
Okay.
Is it okay?
I think someone mic is on, sir.
Mic is?
Yeah, I switched it off.
Oh, okay. So remembering the operator, it translates Q, because P, e to the power of I, P translates the P Q position by a certain amount, and the translation is given by this. So now notice what has happened here. The state system has gone to the state AJ, and the pointer has gone to the state Q plus AJ. And if there were different states, I would get plus 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 this. Now what are we going to do? Make a measurement of the pointer. When I make a measurement of the pointer, this will collapse to the state A. This will collapse to this state, and hence, since this is the full wave function, I will get AJ as the answer. The change in value of the pointer is GAI, is the GAI or GAJ I should have written. And since we know G, the value of AI is determined. If the initial state of the system is not an eigenstate of A, then it can be expanded in terms of I originally took a very simple example, started with this as A, but initial system need not be that. But I can always write it as a combination of all of them. This is my initial state, and it is written in this form. The normalization condition is given by this for the state. The final state now will be for each I should have written I here. Again, it's a typo, because for each I should have a GAI. The final operation is the projection of Q is not due to the time evolution. Now comes the collapse of the wave function, and that's supposed to be due to environment and so on. This causes the collapse of the wave function, leading to a particular outcome. But notice they're all correlated. If I get Q plus AJ, I know the system is in AI. Q plus GAI, I know the system is in AI. So this is where this system collapses, and the collapse part of it we are not discussing. Such a collapse of wave function, referred to as the projection postulate, which we all teach in our quantum mechanics course, is not completely understood and still a matter of research. So this will not be discussed here. Now comes in another concept called the concept of post-selection. Notice we already did that. When we put in the Stern-Gerlach experiment I showed, I had two of them, and the second one was measuring in the horizontal direction. So that was the post-selection that was done there. And that is the new thing that has been introduced by these three authors. The concept of post-selection is needed to discuss the idea of weak measurements. Being an independent concept, we will discuss this first and not go to weak measurements straight away. We will make a measurement on the system such that post-selection of the state is made. Let us start with the state psi s, and let the observable being measured by A, post-selection be psi out. The initial preparation of the state of the measurement is called the pre-selection. Okay, so this is what it is. Now, let me go to the next one. Let the post-selection be made before measurement, before the actual collapse happens. Then the probability pk that the outcome ak is there is the following. Notice, I have psi in, and I am projecting out psi out. This is my selection which is being done. And after that, I get, when I look at the pointer, I get some value for the pointer which projects it out into K. And the probability of this is given by PAK, where n, of course, is the normalization constant to be determined by this condition. This must be equal to 1. This is the selection that I do, 1, n. I'll just wait for a minute. I want to be sure this is clear. Initial system, and this is out, which is what, here it is, out is what is projecting out the state into the out state. After having done that, I observe. When I make an observation, I will get some value K and with this probability. And the system has collapsed into this state. Normalization factor, of course, is given by this. So I can write down the normalization factor. All I have to do is sum over K. Instead of K, I write S here, because otherwise there will be confusion. And this is the expression for that. Now, this A out AS simplifies to the following. I know this is, when I sum this, this is the identity operator. This is the completeness relation. And I have here psi house. If I write this, open up this bracket as this and complex conjugate of that, that is what I will have. And when I have that, I can now use this fact. And so I just get 1. So there is no problem at all. So this equation just becomes psi out or psi n and so much. And so these is the only term that is left is this squared, because this squared has just become 1 and I'm left only with that squared, and that cancels out and I come out with this. And that makes sense, because ultimately when I post selected psi out, I have only a psi out, and then I'm just using that to calculate the probability density. So all this calculation is very common sense thing that we do in quantum mechanics. Now, supposing we make the measurement observation first, I do that. So I get collapse happens here. Now I do project psi out. Then I do psi out this way. Gives the probability of outcome. When I square this, gives out to be again the same. Psi out squared of AK works out. It's the same, because when I do this psi out squared, and that is just 1. For if I do that, this is psi out k squared, and that is just 1. So I just get this. So we get the same answer, whether I make a measurement and then take a post selection, or whether I do a post selection and make a measurement. This was for the special case when I originally had my system in a particular Q. Now we are going to do a different thing. In the special case, the detector was in an eigenstate of Q. Both the outcomes worked out to be the same. Now let us consider in a different fashion. Psi Q is given by the Gaussian here. So let me just go back and tell you what this corresponds to in the experimental situation that we had seen in our earlier slide. I'll just go back and explain what is happening there. And that is crucial for this to work. This beam, which is coming in here, is not without, this doesn't have a single Q. There is a Gaussian distribution of it along that direction. And that's what we have shown in that slide here. That's what I'm going to take now. Here it is. So this is what I take for my Q. So now the final wave function will be, I have sin Q here, sin e to the power this. This part of it is notice only for the detector. This is for the system. This is for the detector. And I write it as QP sin. And I write psi out. And then here I just introduce AK. Then I have sin. And then I write it down. This part of it is what I had said was exponential this much. Okay, I forgot my square root of 4 pi sigma, but that will not matter. Then I write here, continue, This is psi out in psi x right. So this is my psi out. The probability of post selection is given by this expression, psi out. We apply this formalism to spin half. So start a brief review of angular momentum theory. We will assume the knowledge of quantum mechanical treatment of angular momentum. In particular, there are three components which are all operators. They satisfy this famous relation Jx, Jy is equal to IH cross Jz and cyclic permutation of them. That is the standard thing that we do. And this, along with J squared, has positive eigenvalues, and its eigenvalues are given by, this is just, I'm refreshing you people with this, and J can take 0, 1, or half integral values, half, 3/2, and so on. Now I will concentrate on spin half. Here I will take spin half Jz to be diagonal, and that it has two eigenvalues, which are h cross by 2 and minus h cross by 2. And we will represent them by this 1, 0 and 0, 1 as a column vector in the two-dimensional space. The very standard thing that we do. And I will also use the Pauli matrices. The Pauli matrices are given here, all the three of them. This is just to remind you of things which you might have not taught recently. So I'm just reminding you of this. Okay. We will also need the eigenstates of this. Remember, we had done the magnet along the the post selection which was done was along that direction. So I would also need this particular expression where these are eigenstates of sigma plus. Plus is the eigenstate with value +1 and minus is the eigenstate with value -1. Now we are ready. We have all the thing ready. Consider a beam of 3.5 particles moving along the y-axis. This is subject to Stern, which is will split the beam into two. The direction of the splitting is given by the direction of the axis of the SG apparatus. We choose this axis to make an angle theta with the z-axis. I've rotated the SG rather than the particle. Due to this, the interaction with the magnetic field, we assume the particles have magnetic moment. The beam splits into two. The two beams are eigenstates of now cos theta sigma z plus sin theta sigma x with eigenvalue ±1. Why? Because my Stern-Gilrock apparatus is kept at an angle theta. So I have two eigenvalues. So this is the one with eigenvalue +1, and this is the one with eigenvalue -1. Now, projecting out in the state plus theta, which pre-selects the states. Now, the first one is, this is the first one which is done, the weak one, and that selects it into plus and minus associated with the plus in. So I'm only going to take this state. Okay, that's my pre-selection. I'm only going to take this state. And that state can be written in terms of eigenstates of sigma z. These are eigenstates of sigma z. You see that here, I have cos theta by 2 and sine 1 plus sine theta by, this 1 coming from here, and plus theta in will be that minus. Okay. With sigma s sine theta as sine theta in. Okay. You can do the calculation and you will find that. Okay. The Hamiltonian now is given by minus g delta z sigma z. This is the coupling which it has, the magnetic moment has with the detector. This is the direction in which things are going to change. Now, notice I have not used P this time, but I've used Z. That means it is the momentum which is going to change. And momentum, of course, when it moves in the screen, will produce a change in Q in the screen, but we are only going to talk about the change in momentum now. So finally, now this is the post selection which is being done along sigma x. And when we do that, consider only the one which gives the eigenvalue +1. We only take that. And that is given by, thus the final state of the function is this. So I have to take this product. Psi in for the detector is this. Let's collect all the data. Psi in for the detector is this. And psi out for the system is this. We ignore the momentum spread along the x and the y direction. We are only concentrating along the z direction. Now, system plus measuring device. System plus the detector evolve due to the interaction. And how does it evolve? I have phi pz. This is the full thing. Is the detector, I am writing pz, and psi out e to the ijz. And then this is the initial pre-selected wave function here. This is the pre-selected for the detector momentum. There is a spread of momentum there. This is the initial wave function that is there. So this is the entire thing is the initial wave function. And this part of it is the time development. Because there was g delta t, I integrated over t. And the delta t gave me just 1. So I get this is the time development. All I have to do is evaluate this. How do I do that? Sigma z, when it operates on this, gives me +1. So I will get +1 for this state, and that will shift this by pz plus ig sigma ig. Pz plus g, right? Here. And this one will give me minus here. So it will, that term will shift by that. Notice. So the first one is given here, Pg, and the second one is given here. And the normalization, which I have forgotten earlier, is right here. Now, this is the final answer. Now we have to do the probability distribution, and I write this. Okay, if I have taken this, then I will convert this into dimensionless variables, Pz by 2 sigma and this. And notice S essentially talks about the interaction, and sigma tells you about the spread of the wave function, initial wave function, the momentum one along Pz. So I have Fp squared is phi p squared, and that I write it as cos theta p minus. This is completely simplified. We plot this function now for different values of z. Now notice one thing. If I know the strength of the interaction, the amount of displacement that I get will tell me what is the spin of the particle. What's the value, average value of the spin of the particle there when I do it many times over. We will plot this function for different values of theta and s. We will take theta to be 0 to start with. When theta is 0, the particle and the pre-selecting Stern-Gerlach is at 90 degrees. And so that's perfect. And S is very large, then somewhere weak and small. So look at it. When S is infinity, S, theta is 0. Theta is 0, this just is cos, this becomes 1. And that becomes, so this thing is very highly peaked at p equal to minus s. And that one is peaked very highly at p equal to plus s. So I have two peaks. And this, of course, is just 1. And that's also 1. So I have two peaks. One peak at minus s, another peak at plus s. That's the standard thing, which is the one which we normally see, as we see. And now this is occurring at 50. And if I divide this, I would get s is equal to minus 1. And here I will get s is equal to plus 1. Now let me go to 1. Then s is 1, the peaks are coming nearer, and it is still here. And now one can check that the maximum here is also very close to 1, and this is close to minus 1, and still they're distinguishable. When I go here, alpha equal to 0, of course, there is no way in which I can see. And we zoom in this region, and we see the room zine is here. It's peaked around 0 when alpha equal to 0. Now let us change alpha. I have changed alpha to pi by 8, and notice one of them is less, its magnitude is less, and the other one is more. And here the peaks are at -2 and +2, no problem at all. So I get at sigma z eigenvalue is -1 for this and +1. Now comes the difference. When I take s is equal to 1, the peak is no longer at 1, but slightly differently. And here at p equal to located at p equal to -1, and the other one at so much. So here the absolute value of sigma z is no longer 1, but 0.973 for this case. That's perfectly okay. Now comes s. I make s even smaller. When I make s smaller, my interaction is weaker. Interference produces a probability, a single peak, because my interaction is weak, so it is here. The peak is at 0.184. I divide this by 0.5 to get the value of the sigma z average, and that's 0.36. No issues. Now come here. When s becomes very small, I divide this by, so I get 2. So this gives me an answer larger than 1. Right? Did I say it right? Not yet, not yet. Sorry. This is still 1/5. Am I correct? Yeah. P by S is 1/5. Now I go to larger angle smaller, then make it alpha equal to -pi/4. And here I have 2 peaks. S is equal to -2, and equal here because S is still large. I make S small, and P is at -1.497. So sigma z has become -1.497. The other one has become that. Finally, I make S very small. And when I make S very small, in this case, notice the peak is at 0.049. And if I divide that by 0.01, the average value is 4.9. So I would say the spin is 4.9. And they have the plot used by Aronoff, etc., have been able to extend it up to 100, the average to be 100. So the measurement of the z component of spin is being done by the position of the peak probability and dividing it by the strength S. Thus, for large S, we find the values of the spin as ±1. In the table below, the position of the peaks for different values of alpha and S are given. Okay, let's look at this table. Alpha S. Alpha is 0, 50 minus. So peak here is here. It's clear. So now again, I made alpha less. Alpha is 0. I get this. No problem. Everything is exactly the way we teach in quantum mechanics. Now take pi by 8. S is 1 minus 1. This is 0.973 and 973. And this is just value is -1. Peak 1 is -1 and peak 2 is at 0.973. Again, no conflict with our normal thinking. Here, when I go 0.5, I get 1.18. And so the average, there is no peak here. There is only one peak, and that's at t equal to 3.8. Because my S has come down, the 2 peaks are merged. Now I go to a different angle, 0.4. I put 1. I have here minus 1.4702. And now notice things are no longer in the range -1 to +1. And when I keep decreasing it, this number goes beyond the region -1 and +1. This is the result of the 3 famous authors. Now, I've done it with an example. Let me just write this in terms of an interaction Hamiltonian and formally develop it. I write it in this form. So I write down sin psi I out. This is the expression, which is the exact expression. But I'm going to expand now, thinking G as a weak coupling constant, and expand that exponential and write it as psi out, I cross I, Ig, A cross G. Then I pull out this psi G and psi out and write this as A weak. Psi in for the detector is not, we are now only talking about the system. So the system is A weak is nothing but psi out, A psi in. Here notice psi out, A psi in. And since I pulled this out, I have to divide by the denominator. This is the definition of weak measurement. This is the formal definition. Notice this value is not even Hermitian because psi out is not equal to psi in. So we do not, this will be a complex number in general. So people question whether this can be considered as a genuine measurement. Peak values are in general complex. In our example, the real part gives the shift of the pointer position. The imaginary part gives the shift of the momentum. I'm not going to derive this. It can be derived, and the references I have given, those of you who are interested can go through this and you will find that. Again, these are absolutely standard quantum mechanics. There is nothing different, but the effect seems to be very disconcerting and very deep. So peak values of an observable A can be outside the range of the eigenvalues of A. Normally, when I make a measurement of any operator A, the maximum value it can obtain is the maximum eigenvalue of A, and the minimum is the minimum eigenvalue. When I take the average will be somewhere between minimum and maximum. Not so here. So that is what was the dramatic thing which caught the attention of people. Okay, spin a half where we have sigma A is sigma z and A squared is 1. So I can write this as e to the power of I cos IA sine T. It is straightforward to write this A. Right, this is the standard thing we all teach at MSc level. So expectation value of any operator is initially at psi in, and similarly psi out. The difference between the two gives me the shift in terms of AW. I will not derive this in any great detail. I'll just write it down. M for the out state is given by the following expression: cos GP plus AW squared sine GP, M, the expectation value of M, and here IAW sine M cos P, and here sine P. This is the general expression from where you can evaluate anything. It's very, I won't be given the general one, but we have worked out the specific case, and this is not very different from the specific case that we have looked at. Okay, the averages have to be taken in terms of the states that we have. Okay, and A weak, of course, is where the psi in and psi out merge together and come out. Now, the several experiments have been performed using optical interferometers over the last 2 decades. They have confirmed the above analysis. I will not discuss that here. How to exactly make this is quite a bit of an experimental skill, and a lot of work is published, and it's not very easy to follow these works. So I will not be able to discuss them in any detail. Further, the weak values can be used to amplify signals where the coupling constant between the state and the measuring apparatus is weak, like gravitational interaction. I will not show how such an amplification can take place, and that is the thing which is a very interesting application, and it takes a lot of calculation, and that itself will be a subject matter of one more talk. So now I have references. Here is the first reference, and this paper, the second paper, first paper is in Physical Review Letters, is rather, at least I found it quite, I needed a lot of effort before I could figure out all the details. But this second paper explains everything very beautifully, by Duck, Stevenson, and E.C. Sudarshan. It's a very, very beautiful paper. Then there is this paper in Scientific Reports, which broadly explains these things in detail. There is one more experiment which seems a very interesting one, already performed and done, and it is this. Supposing I take a double slit and then use polarized photons and try to measure the weak measurement. Normally, as when I just started the talk, I said the polarization, when I do a double slit experiment, then if I try to observe which path, interference is gone. Here, they have been able to achieve the following. They can get the average trajectories of all these particles which are there, and then they can also show the interference exists even then. So that they know for average the trajectory of this particle is along one of the slits and the other one is along the other slits. They can figure that out, and the interference pattern is still on the screen. This, of course, does not violate the statement that you know for sure which particle went through which slit destroys interference. That part of it is not questioned here. So these kind of experiments are continuing, and mainly because technology is also improved and many exciting results associated with this are coming out, and many applications are also, I'm sure, will come out more. I think that's a good place for me to stop, and here, thank you.